Let's look at question 1, Bernoulli Equation application. We are told that water is pumped into a delivery tank from an open suction tank. It's important to realize in this question that the delivery tank, which is closed, can sustain a pressure of 250 kilopascals, absolute. However, in the suction tank, which is an open tank, the maximum pressure, or in any case, the only pressure it can sustain is atmospheric pressure, which is in this case 101 kilopascals, absolute. So when we do Bernoulli's equation, our starting pressure at the point 1 will be 101 kilopascals. Our delivery pressure at the point 2 will be whatever pressure that the tank can sustain. In this case, since it's a closed tank, 250 kilopascals. Let's get back to the question. If you now look at the rest of the question, you're given the pumping arrangement, which you should study very carefully in figure 1, and you are told that all valves are in the open position. In this question, it's not really necessary to know that fact, other than the point that you don't have to worry whether the valves are at any intermediate position where there are friction losses that usually are higher than in the open position. Now let's look at part A. While the flow velocity in the suction pipe and the delivery pipe, you are asked to verify that indeed both velocities are the same. Next, you are given the volumetric efficiency, and in this case the volumetric efficiency is, the volumetric flow rate is 6 meter cube per hour. Let's get about solving part A now. If you look at part A, you are given that the diameter of the suction is 30 millimeters. The diameter of the delivery pipe also 30 millimeters. Now, from continuity, very important, AS, A, the area of the suction, times V, the velocity of the suction, is equal to A, the area of the diameter, the area of the delivery multiplied by the velocity in the delivery are equal. Therefore, it follows that the suction velocity is equal to the delivery velocity because our two areas are the same. Now let's look at the second portion where we are supposed to calculate the velocity in the pipes. You're given the volumetric flow rate as equal to 6 cubic meters an hour, divide by 3,600 to change from minutes to second, and you get 0.0017 cubic meters per second. So using the formula that velocity is equal to the volumetric flow rate divided by the area, we plug in our numbers, in this case 0.017 divided by the area, and we get 2.41 meters per second. Now this is a reasonable figure as we looked at flow in pipes in the lectures. You were reminded that the velocity generally is between 5 meters to 1 meter per second. So this is a reasonable value. Now let's proceed with the part B now. If you look at what is required in part B, we are supposed to use Bernoulli's equation with pump head HP and losses in the friction in the pipe and fittings HF, which is given by the formula K into V squared over 2G, where K are all the losses relevant to whether we are talking about the suction or the delivery pipe, and we are supposed to determine the pump head. Okay, let's tackle part B now. If you look at the Bernoulli equation, taking from point 1 to the point 2, point 1 here to the point 2, let's trace a streamline from point 1 to point 2. So using my marker, I will trace a streamline. We start from 1, the streamline takes its path from point 1 up the suction pipe into the pump, through the valves, down the delivery, right down to the suction, to the delivery and up again. So that would be the streamline. And if we now look at Bernoulli's equation, we start off with P1 over rho G plus V1 squared over 2G plus Z1, all related to point 1, plus the pump term, which is our little pump here, plus all the conditions at the end of the streamline 2, plus any losses that we have moving from point 1, the suction pipe, and the valves and all the fittings. And we are given that the losses in the suction pipe amounts to a loss coefficient of 3.0, and the losses in the delivery pipe amount to 4.5. So what we do is we now make a very important simplification. we should study very carefully. Now this simplification says that V1 and V2, the velocity of the water level at the point 1 and the point 2 are significantly smaller than the velocity in the pipe, suction pipe, and the delivery pipe. Remember, we calculated the velocity in the pipes as 2.41 meters per second. So what we are saying is our zero is preceded by a very small value here. It's not zero, but the level falling, the velocity of the level falling is very, very small. And here the velocity of the level rising is very, very small compared to what? Compared to the velocity in the pipe, suction pipe and delivery pipe. And hence we can make this simplification. The other point is, if you study the figure 1 very carefully, you will notice that the suction water level and the delivery water level are identical. So they are in fact zero, the difference in their levels. So the equation now simplifies as shown here. The rest is a question of plugging. P1 minus P2, P1, in this case P2, sorry, P2 minus P1 okay, plus the total losses, which is 4.5 plus 3.0 to give you 7.5, multiplied by V squared, the velocity in the pipe, divided by your 2G. And when you add them up, you get 17.41, which is the water head, which is the pump head required. Okay, what we have done is the pump head required is 17.41 meters. Now, in the part C, all we are asked to do in part C is to calculate the pump power in kilowatts, and you're given that the pump efficiency is 60%. So, let's get started with that. The pump power is equal to the density. Now let's get the point here. The density multiplied by G times the pump head times the volumetric efficiency divided by the efficiency. Plug in the values and you get a value of 0.484 kilowatt, and that's it.